Hello everyone, welcome back to the channel. Today we will be solving round 975C cards partition, where you are given some cards. An integer between 1 and n is written on each card, and you have a of I cards with number I written on them. So first thing to notice, you have a of I cards with number is equals to I. Okay. Then you need to partition all your cards into decks. Okay, all your cards, not some, all your cards. This is very important for our solution. You have to partition all your cards. Okay, now you can buy at most k new cards of any number. Okay, so that's the extra cards that you buy. All decks must be of same size. All decks must be of same size. And all decks one deck should have all distinct numbers. So these are the conditions to build your decks. You have to find the maximum possible size of a deck after buying cards and partitioning them optimally. Okay, now the first thing to notice, almost everyone in this problem has thought for binary search on answer. But that will not be suitable because first of all you need to partition all your cards. That is very important. Okay, so let's say that you have some decks of three size, one size, and one size. So this is not allowed. Okay, you need all of the decks to be same number of size. Okay, and need all to be distinct as well. So why not binary search? Because the function is not monotonic. Okay, the function is not monotonic, hence we can't use binary search. So what can we use? We can use greedy. What we will do? We will check for each answer is equals to I from 1 to n, and the maximum answer from all of that will be our answer. I see, this is what I've done. From all answers from 1 to n, I have checked whether it is possible to partition that or not. And if yes, I am choosing the max of all of those answers. Okay. Now the thing to think is, how do we implement this check function efficiently? Because already we are calling this n times. So this check function cannot be more than log n. Okay. This is what we have to think. Okay, now I will explain you this test case because this is the test case with which I understood the answer with. Okay, I'll paste it here. Okay, so this test case means you have two cards of number 1, 6 cards of number 2, 1 card of number 3, 2 card of number 4, and 4 cards of number 5. Okay, so let's try to make our deck, and I can see the max answer is 3. So let's try to check for 3. Since my maximum is 6, I will stack it down 1 2 3 4 5 6, and since my maximum is 6, I compulsorily need to have 6 decks or more because all numbers have to be distinct. So I cannot have two sixes in one deck. Hence minimum I will have to use the max number of decks. Okay, that's why I am calculating max. That is going to be very important. Okay, now above 6 what can I place? I can wait, this is not 6, this is 5, sorry, this is 2, 1 2 3 4 5 6, 6 cards of number 2. Okay, 4 cards of number 5. okay, and 2 cards of number 4. Then I have 2 cards of number 1 and 1 of number 3. So if we carefully look, I need 3 more numbers to complete my stack of 3, and my k is 4. Hence this is a valid answer. Now how do I check this? I know my max is 6 and I want to check for 3. So I will at least need 18 cards. And if my sum is less than 18, which means I will buy 18 minus some cards. This is the logic what we need to implement. If we need 18 cards and we have 15 cards, so we need to buy 3 cards, which is less than equal to our k, and hence our answer for 3 is true. Now the important case, what if we need 10 cards and we have 12? Then what should we do? Then what we will do is we will increase number of stacks by 1. Let's say we have 5 stacks. No, let's say we have 6 stacks. Okay, and we have more than what we need. So we increase our stack by 1. So automatically our need increases by that many of cards. And we will have to increase the number of stacks as much times as our need is less than what we have. Once our need increases our have, my k would be minus equals to need minus have, and then I just return k more than equals to 0. So now this operation can be easily written by while need is less than have, need plus equals to, let's say we are checking for I, so need plus equals to I. But the thing is, this will lead to TLE. But we know that this function is monotonic. So we can apply binary search on this to find how many times we need to increase our need. Okay, now I'll show you the implementation. I have calculated the sum and our max of our input. Okay, now our check function. Target is what we need, that is maximum into answer, and present is what we have, sum. Now in the binary search, basically I am doing this. While need is less than have, I add need by I. This thing brutally will give me TLE. So I am opting for binary search to know that how much I would have to increase my target by so that it is exceeding or equal to my present. Then I will actually increase it by exactly those many of times, and then subtract k by how much I need. And then if k is still more than or equal to 0, my answer for that particular I is true. Okay, and then the maximum value of n of I that satisfies this check condition will be my final answer. Okay, so thank you guys for watching. Make sure to like, share and subscribe to never miss another tutorial.